In the realm of cancer diagnosis, predicting a patient's response to treatment is crucial for improving survival rates and treatment outcomes. This paper proposes a novel methodology for predicting the treatment response of diffuse large B-cell lymphoma, DLBCL, patients from whole slide images, WSI. The method leverages several foundation models as patch-based feature extractors, aggregating these features into a local representation of the image. A global representation of the WSI is then obtained by aggregating these local representations using attention-based multiple instance learning, MIL. This technique is chosen because only WSI patches representing tumoral or stroma tissue are relevant for predicting the response. The proposed method is distinct from recent work by Lee et al., which uses a vision transformer model exclusively trained on their own private dataset. In contrast, the proposed method produces a prediction model that is not only trained on the author's dataset but also leverages representations learned from large-scale histopathology datasets through the use of foundation models. This approach emphasizes the potential of foundation models for characterizing histopathology images and generating more suited semantic representations for this task. The research paper formulates the task as a binary classification problem, where the goal is to predict the treatment response based on the patient's Deauville score. The proposed method utilizes multiple foundation models, pre-trained on large-scale histopathology datasets, as feature extractors to produce low-dimensional embeddings from patches of the WSI. These embeddings are then aggregated using a patch-level aggregation function, defined as the concatenation operation, to create a single representation of the patch. This approach allows for the utilization of diverse representations induced by the foundation models and minimizes the risk of losing information. The aggregated embeddings are then treated as a bag of instances, and an attention-based aggregation function is applied to create a WSI-level embedding. This function assigns higher importance to patches that most contribute to the prediction, inspired by the work of Ilsa et al. The aggregation function is defined as a parametrized function, noted G, which takes the aggregated embeddings as input and outputs a weighted sum of the embeddings. The weights are computed using a neural network with a tanh and sigmoid activation function, which allows for the assignment of higher importance to relevant patches. The output of the aggregation function is a WSI-level embedding, which is then used to predict the treatment response. The proposed method is evaluated on a dataset of WSIs with His staining, and the results show that the approach achieves state-of-the-art performance in predicting treatment response. The use of multiple foundation models and attention-based aggregation function allows for the effective utilization of diverse representations and relevant patches, leading to improved performance. The paper also discusses the limitations of the approach, including the lack of fine-grained labelization of the WSI and the assumption that all patches are not equally relevant for treatment response prediction. Future work includes exploring other aggregation functions and incorporating additional features to improve performance. This study explores the application of foundation models in predicting treatment response for diffuse large B-cell lymphoma, DLBCL, patients. The proposed method aggregates patch-level features from whole slide images, WSIs, using two foundation models, CONC and HIPT, and compares their performance with a standard ImageNet pre-trained ResNet 50 model. The two-stage aggregation process involves extracting features from each patch using foundation models, aggregating them using a concatenation function, and then forwarding the aggregated feature to an attention-based WSI-level aggregation function to predict treatment response. The dataset consists of 384 WSIs from 152 patients diagnosed with DLBCL between 2010 and 2023, with treatment response evaluated using the Deauville score. Experimental results show that foundation models outperform the ImageNet pre-trained ResNet 50 model in terms of accuracy, precision, recall, and F1 score, with the best performance achieved when combining features from both CONC and HIPT models. However, low specificity results indicate that identifying negative responders remains challenging. Comparative analysis with other methods, such as DTF-DMIL and trans-MIL, demonstrates the proposed method's superior performance, with a ROCA-UC gain of 4.5% and 7.6%, respectively. The study also compares different aggregation functions, with the proposed method outperforming others in terms of ROCAUC, FS-score, and specificity. The results highlight the potential of foundation models to improve patient outcomes in clinical settings, and further investigations on aggregation methods and new foundation models are encouraged. The proposed method's success demonstrates the effectiveness of exploiting foundation models pre-trained on large-scale unlabeled datasets with self-supervised learning in computational pathology. The authors present a comprehensive review of existing literature on diffuse large B-cell lymphoma, DLBCL, emphasizing the importance of accurate diagnosis and treatment. They highlight the need for robust models that can predict patient outcomes, citing studies on the use of artificial neural networks, ANNs, for predicting overall survival and molecular subtypes of DLBCL. The review also covers the application of vision transformers for gigapixel image analysis, self-supervised learning frameworks for histopathology, and deep learning models for DLBCL diagnosis and prognosis. The authors emphasize the significance of understanding the molecular subtypes of DLBCL and their impact on treatment outcomes, referencing studies by Nowakowski et al. 2015, and Sees et al. 2004. They also discuss the development of whole slide image classification models, such as Transmil and DTF-DMIL, which have shown promising results in classifying DLBCL subtypes and predicting patient outcomes. The review underscores the importance of interdisciplinary approaches combining computer vision, machine learning, and oncology to improve diagnosis and treatment outcomes for patients with DLBCL. It provides a comprehensive overview of the current state of research on DLBCL, highlighting key findings and methodologies from various fields.